It is a great honor to give this talk, and of course, a lucky coincidence that the Nobel Prize was yesterday given for attosecond science. It is also an honor and a pleasure for me that so many of you were interested in that, and I hope I can, try to transmit some of the excitement that many of us have for probably 1 or 2 decades, working hard on all kinds of different tricks and nonlinear optics and extreme lasers to not only make these pulses, but also have a vision of what they should be used for. And what I try to tell you a little bit today is what my motivation was over all these years. I thank you, Giulio, for being so nice with introducing me on that. Of course, it's an honor by being introduced by such a pioneer in the field himself. And I try to tell you a little bit the ingredients there, and then something that I'm very excited about, which are actually quite recent and nice results, where we really apply them on something that is fundamental, of fundamental interest in solid state, but also on molecular science. And I think that can, where you don't need 30 years to bridge some application, but where you probably can influence something very soon or very quickly. Let me see if I can switch the slide. Okay, you can see this. So thank you. I just want to mention before I start that as former executive director of Laser Lab Association also, I thank the office and Ramona for the nice intro, and ICFO, but also Politecnico Milano and many others are places where you can have access to. You can write to us and you can ask if you want to do some experiments with us, and you don't have to be in the European Union to do that. Okay, let me cut to the core here. And I want to give you 4 quick examples on why I think we should do something different, or where I think that it is worth going through all these troubles. Attosecond science, let's be honest, is complicated. It involves a lot of hard work and money to build these kind of systems and sources. But what can be done? I give you 4 examples. The first one, very quickly, energy harvesting, let's say organic solar cells. You know that the efficiency, okay, is a bit more than 15% now, but not much more. Range around 15, 18% or so. And we really don't know exactly what to do in order to increase it. So, of course, many people work on that. And I don't want to step on anybody's feet, but it's still the matter of fact that we haven't solved this. And maybe there is an intrinsic fundamental problem, or we don't really know what to change in the material synthesis to address this. And so what could be the issue? So I've shown you here, maybe I don't know if you can see probably you can't see the cursor, but you see the little sun symbol, and then this subphthalocyanine and chlorine complex drawn on it. And in the middle, there is a little green dot, which is a chlorine atom, which acts as an antenna complex. So what happens there is that it absorbs a photon, let's say from sunlight, and it generates an electron-hole pair. And then somehow these kind of carriers need to propagate. So there's transport, there is absorption. And then, of course, you want to store the charge somewhere, maybe in your batteries. And so one question could be, is the electron-hole pair generation an issue? Then, of course, in these organics, you have a low dielectric constants. You have a lot of exciton physics. So these electrons and holes, they can be strongly coupled. So then the question is there transport? So one simple Gedanken experiment, maybe it's too simple, but you can imagine if there is something happening at the chlorine atom, and you had a way to monitor only this chlorine atom, you would probably register some change in absorption there. Then if you could distinguish, for example, through X-ray or soft X-ray absorption edges, for example, the neighboring atoms in this case are nitrogens. So if or when the charge moves across this backbone, across the nitrogens, you might see some that is registers by a change in absorption at the nitrogens and at the carbons and later. So this could even be a way to look and to connect actually time resolution with spatial resolution on an atomic or subatomic scale, and see if we can learn something about the absorption or, for example, the transport. I give you quickly two, three other examples. Another one is, of course, chemical functionalization is actually the backbone of our civilization. Actually, nearly everything is made out of crude oil or products thereof. And how chemical industry synthesizes things is, of course, important in order to make things. But also the energy that is spent on it is considerable. It's about 19-20% of the global energy budget. So if you could do anything, for example, polymerization, making plastics, if you could just reduce some thresholds for this by a few percent, I mean, you have a huge impact environmentally. And of course, for companies, they're interested because you could save billions and billions of euros or dollars just by such a small change, in fact. And of course, it's a big dream of chemistry or physical chemistry, even though most of it is probably photochemistry that we're doing to look at this. Another one, that's actually a very interesting one, is electronic transport. If you look at, for example, your iPhone, or if you look at internet devices, for example, that transmit information, at some point you have electronic circuits, and they work basically by moving carriers, ideally through ballistic transport across junctions, and then you need to save some information or store it somewhere. And currently about 12 to 15% of the global energy budget goes into this. This is considerable. And any prediction, or at least that's a prediction from 2019, and it's probably going to be worse, is that this rises to 20% of the global energy budget until the end of the decade, despite global warming issues. And then we have also developing economies. And of course, you cannot expect them not to take advantage of this information technology. So that's a serious issue. So if we could, for example, find out how we can move these carriers potentially, or do computations much more efficiently, or not, for example, coupled to the lattice, produce heat, which is just loss in this case, you could have a big impact, and it's actually important. And so, of course, many people work on all these subjects, not just us. And then if you think how to address these big standing problems, of course, you come across new discoveries just by accident. Like, for example, this tristronics, right? That you have this magic angle, in this case of graphene, and you can mimic some transport properties like superconductivity and maybe use this in the future for some applications. But if you really want to address these kind of issues that I just motivated, we should try, and we should be striving to develop analytical methods that allow some engineering approach to this, and not just basically a discovery based on serendipity. So what I'm trying to sell you here and convince you of is that attosecond technology is not the solution to everything, but it's a powerful new technology in the tool of material scientists, chemists, and others that gives a new view. And I strongly believe in this, and I hope I convince you of this during that talk. So let's say what unifies all these issues that I just mentioned. And if you go to material science talk, they show you something like this typically, which is basically the coupling between electrons, nuclei, and spins. And then many times we say, well, electrons, they move very fast. Nuclei, let's say, are 2,000 times heavier, roughly. So this should be on a totally different time scale. And spins are slow anyways. However, this is not really true. This separation in chemistry, it's called Born-Oppenheimer approximation, for example, between electrons and nuclei. Whenever, I would claim to you, whenever interesting things happen, phase transitions, structural phase transitions like isomerization, adiabatic dynamics, conical intersection, charge migration, mod physics, there are many examples of this, then this exactly happens when these things are strongly coupled. And they might be strongly coupled over longer timescales than we think. So then the issue is that we have a lot of different analytic methods with which we can look at them. For example, you can use photoemission spectroscopy, but you might not really look into the bulk, or you might only get indirect information about nuclear vibrations. If you use, for example, Raman spectroscopy, you can, of course, get nice information about lattice motion. However, only about the phonons that are Raman active, and some others are dark to the technique. Or visible spectroscopy gives you incredibly good time resolution, or 2D spectroscopy, but it might be difficult to disentangle some of these contributions. So the issue then is also, if you piece this information together using these different methods, they many times require different preparation of these samples, and this changes how these samples react or what you can measure with them. So one solution, not the only, but one solution that I'm very excited about is that these attosecond pulses, especially soft X-ray pulses, allow you to address this in a different way by the fact that you have a short time wave packet, a photonic wave packet, but you have also a coherent large energy spectrum that you can use together. And I'll try to get a bit into this in the next couple of slides. So let me spend a few minutes on the attosecond technology itself. So of course, it's fantastic, and it's exhilarating to see that after the Nobel Prize for CPA in 2018, that this was recognized. I mean, the generation, in fact, was recognized. And let me just give you a very quick feel of what we're doing here and how we can use this as a light source. So what I show you in this little movie is a calculation I've done for you, which shows the ground state of a noble gas atom. It's a p state. That's how it looks like in the field-free case on the left. And then what I show you is different snapshots in time when you apply a well-controlled, strong laser field. And what it does is, of course, what you learn in physics classes, when the field gets stronger, you distort this electronic density, you induce a dipole, if you will, but you're still in a bound state. If you increase the intensity, so that's, let's say, a little bit past the second one, where you already ionize, you increase the field strength further, and you can actually you pull out some electronic density. Classically, you would say you kick out an electron. I would imagine it rather like chewing gum, that you pull on this wave packet and you pull it apart, you pull something apart, and it's still connected, right? Like a string. Then, of course, if you have a laser field, the laser field oscillates in time. That means it changes literally the direction of the field vector, and it can bring this electronic density that you pulled out back. And then it interferes, of course, with the leftover part of itself in the ground state. And that leads to interference, as you see in the third and also in the fourth frame there. Now you can imagine these interferences. What's the size? How can you use this? Can you use this for imaging? When you have so you have a likelihood for recombination, which is very small, 10 to the minus 8 or so. But consider that you have maybe 10 to the 14, 10 to the 15 photons. So this is non-negligible. So you can use this as light source, and these are the attoseconds of the X-rays that we're using. But mostly, actually, it scatters, and we can also use this as a source of electron scattering. So in this three-step model that people always show, you can visualize it as such. You have the field-free case with the bound state electron wave packet. You distort this potential by applying a field, and then you can have actually excursion, recollision, and scattering. And never mind the exact numbers here. We have these units of ponderomotive energy, which is just a way to characterize this laser field. This depends on the intensity and the wavelength squared. That's important, as you will see later. And then if we ask what are the maximum photon energies that we can generate with this kind of source to produce photons, it's 3.2 times UP. And if you want to use this as an electron source, you can also do that. And because you have backscattering, you have a larger momentum transfer, and you can go up to 10 UP. So why is this challenging, or why is it interesting? Well, it's interesting because you can control things on a sub-cycle scale of the electric field. And if you're at 800 nanometers, one cycle is 2.5 femtoseconds. Half a cycle during which this happens, half a cycle to one cycle roughly is half of it. So it's actually could be bursts of short time radiation. However, this depends extremely on the exact field amplitude and how it changes in time. That means in order to play these games, you have to make intense laser fields. Many times you want to do this only a couple times, so short laser pulses, and they need to be really stable. So you cannot accept fluctuations of, let's say, 10% or 5% or something, depending on what you do. And the exact field waveform, whether the field oscillates like a cosine or sine or something like this, changes the outcome. So you need to have full control over this. And then, since this is not very likely to happen, I already alluded to it, you have low cross-section for this to happen. You want this to happen many times, so quickly, high rep rate lasers, and you need high power if you have high rep rate with high intensity pulses, and that's difficult to build. I highlight some of the papers down there, actually also the middle one that's many times ignored, of the first theoretical description of this process. So just maybe one propaganda slide from my side. So this was actually the reason why we started long time ago to build these laser sources, because they're not easy to actually just have off the shelf. Right? Anybody who works on lasers knows that if you want to have high rep rate and you want to have intense and short pulses, this is where things get damaged. And so you have to be very careful how to do this. And there's not a surprise that the Nobel Prize was actually given for the frequency combs, which is just the other side of the coin of saying carrier envelope phase stable pulses, or as I said it to you, reproducible electric fields under the laser envelope. And then short pulse amplification. Just actually yesterday, the culmination of that to make these short light pulses through the recollision process I just explained to you. So over the years, we have been building all kinds of sources, and I don't want to talk about this. I just want to say that a lot of it, because of this lambda squared scaling, is at long wavelengths. And we have even driven this to the extreme with a 7 optical octave spectrum from about 250 to 40,000 nanometers, which allows you then to take different parts of the spectrum out and have complete coherence and control in time in terms of pump and probe for these experiments. So let's go back to this quick picture that I showed you. So if I take one of these frames out and I put numbers on that, just to give you a bit of a feeling, the Breuer wavelengths you might have is on the order of an angstrom. That's 10 to the minus 10 meters. This wave packet is chirped, as you can see. That has an important influence, but can be used to map time to frequency, if you think about it. And then if I just look at the spatial excursion, let's say the half wave is around 5 angstrom for some parameters that I've given here. So you can already think a typical diatomic molecule, let's say, has a distance of about an angstrom between the two nuclei. So you could use this eventually as a scattering method to measure nuclear or atomic positions. Actually, if you ask yourself what's the current that this represents, it's humongous. In fact, it's 10 to the 11 amperes per square centimeter in terms of electron flux. So it's a strong source of coherent electrons that you can use also. And I showed you below the first spectrum that we made here when I moved to ICFO in 2009. We were very happy. And you see these individual harmonics, this process that we call high order harmonic generation. So this is a frequency up conversion process through the recollision. And if this happens in a time sequence of different pulses, Fourier transform tells you that you get actually a modulated spectrum. Now, if I move and I go to 3 microns to the mid-IR, you see how the numbers change. That's actually interesting because the de Broglie wavelengths goes tremendously down, 6 picometer, and the spatial excursion is larger because of diffusion of the electron wave packet. So you can even look at large molecules, and we have done this also. We can even image each atom in a Fenton molecule, and the recollision energy goes up. This is nice, and many people in the field have looked at different aspects in general of attosecond generation, and it is actually gives you, I would say, one of the only and tabletop sources of fully or highly coherent spatiotemporal coherence. So it's really a time-space wave packet. It's not just like a light bulb. You can make short pulses with it. I insist, and I will say it a couple of times more, it's more important that it's not just a short pulse, but it's also a coherent energy spectrum that you can use to encode signatures of the things you want to look at. You can control the polarization, you can make it huge bandwidths, and very nicely, it's fully optically synchronized with pump probe. So if you really want to trigger some processes and then time resolve them at the absolute limit, you have very little timing jitter, basically. And this is one of the first spectra that we made many, many years ago, showing that you can actually really scale this to the water window up to above 500 eV. And so what we have now by using this technology is that we can make very short pulses of light. Why is it important? Because I want this recollision process to happen only once. If it happens only once, it emits only one burst of radiation, so single attosecond pulses. They can give me a tremendously broad spectrum, like shown on the right in the blue box. These are typical spectra that we have in the lab here on the tabletop. And if we use not the light emission, but the rescattered electrons in the middle, in the green box, you see we can use this really to image molecular processes. And this is, I'm very excited about this too, because you can image a single molecule with one of its own electrons. If you think about this, this is like the molecule taking a selfie of its own structure. So I have told you how we can make the short pulses. The short pulses come with a broad spectrum. How can we address these problems that I mentioned to you at the very beginning? One of the techniques that is extremely well established, especially in synchrotrons and also in other light sources, you can also have it on a tabletop with partially coherent X-rays, let's say, is X-ray absorption spectroscopy, which has a long history. I don't want to get in all the details. The credit has to go to many, many people. You see it, first attempts or discoveries go back to 1913. And what basically in a nutshell, what you see is that each element has its own fingerprint, if you will. So this arises from addressing the 1s electrons, the most inner bound electrons, for example, that you take out of the material or put in a bound state, and that leaves a dip in your spectrum, or when you ionize, you have an edge and a big change of it that's shown here. And so you have from these different electronic innermost bound levels, and since they're different in binding energy, basically like fingerprinting of the different elements that you have in the periodic system. So this is an extremely powerful analytic technique that's used everywhere and all the time, I would say. And why is it so interesting? Not just if you think you have a single, let's say, carbon or titanium atom. If you, for example, go to molecules, you see just by how the atoms are arranged in space, they interact through Coulomb forces, they shift the electronic levels that the system has. And so the absorption edges are different in simple terms. Really, even if you just even change the chemical state of some molecule. And so it is really a nice analytic technique. And I show you here just on the right, the example, if you change the different molecular orientation, this changes very much. So there's a huge amount of body of work on this. Now, what I'm trying to convince you with that we can now combine these attosecond probing capabilities with the powerful techniques that were well established in X-ray physics. And this is traditionally done, as I said, for example, in synchrotrons. I show you in the picture the one here behind the hill. This is ALBA. This is one of the synchrotrons. There are many of them around the world. What I insist on is that, think about it. We use photons. We send them through some system. We measure the absorption of the light. And we want to learn something about carriers. So it is very important that either through theory or through some clean experimental connections between the charges we probe and the photons we measure, we can make clear statements about what we're trying to measure here. And in order to do this, you have to use the fact, for example, in a system, I show you here some artificial carbon atom. Most of the chemistry is done in the valence shell. This means the the electrons that are just below the ionization threshold, or in molecules, or in solids, let's say just below the Fermi energy. This is their occupation changes, they move around. Now, if I want to probe their behavior, their state, with X-ray spectroscopy, I should use some electrons from the same element, but ideally as far away as possible from them. They should be screened. And I do this by going to the most innermost bound electrons and not just using, for example, the 2s shell to probe the 2p shell. I should use the 1s. And the difference is not here to scale. The difference can be, let's say, a few eV, 10 eV between 2s and 2p, but between 1s and 2p, it's 300 eV. So there's a big difference. So how does this work? Well, let's assume you go to a synchrotron, you ask for monochromatic or relatively narrowband radiation, and you sweep the photon energy. At some point, you hit a resonance because you can move the 1s electron to the 2p state. And when this happens, you will see a change in the absorption. And so you can imagine if you have something more complicated than what I drew here as example, you can really interrogate the whole electronic structure, at least of the non-fully bound or not fully filled electronic shells or bands in materials. Once you increase photon energy further, you can kick out the electrons into the continuum. You photoionize, that's always possible. So you have a big change in absorbance. And then if you don't have a single atom, but let's say you are in a molecule or in a liquid or you're in a lattice, you have neighboring atoms, and what this does is they talk to each other. They change the scattering and the absorption cross-section, and this manifests as modulations in the absorbance spectrum as shown here. And of course, X-ray spectroscopy, the people have spent a lot of time really trying to find out what they can get out of this in terms of information. They have given this names, for example, X-ray absorption near edge structure, from which you can mainly get the electronic information, and extended X-ray absorption fine structure, from which you can even get basically the nuclear configuration, but a lot more as written there in blue. And we have used the fact that when you make these short light pulses, they come with a humongous spectrum, 200 eV or even more. This is typically a problem, but here it's a blessing, because you do not need to tune the photon energy. In fact, you cover it at once. So you can cover this whole spectrum in principle at once, and you don't need to tune anything. And you only have to worry about pump probe time resolution, for example, to interrogate then the dynamics. Now, that also tells you that you can actually get electronic and potentially nuclear dynamics at the same time. And if you remember in my motivation, I said one of the challenges is to see how electrons, for example, and nuclei interact, and especially when they're strongly coupled. Now, if I measure only one of them and I want to learn about the others, but they're strongly coupled, I would need to know these couplings. And this is very complicated. This is many-body physics. Now, if I get the overlapping signatures of both of these at the same time, I have an overspecified system in a sense, and I can think of really trying to disentangle this. So we have shown in the first measurements, they were not time resolved yet, but we have done this also 2 years ago, that this can be actually done. So just quickly on the source. So what we have is basically a 2 micron source at 1 kilohertz. We don't want too high repetition rate because we want to look at solids, and you don't want cumulative effects of heating the material through the pump. So too high rep rate for that is not the best. The experiment then to make these attosecond pulses looks conceptually simple. There are many details, and if you want, ask me later or have a look at some of these papers. We essentially focus this intense laser pulse that is sub-2 cycle CP stable. That means the electric field is fixed to about a few 10 to the 14 watts per square centimeter. We ionize, we have recollision, recombination, emission of light. And then we send this maybe through a sample and collect it or analyze it on a spectrograph. And then the real experiments are, of course, pump probe experiments. The problem here, when we actually did this, we were the first to show this concept that it works, because attosecond science was actually working around 20, 40, 100 eV, and still most of it is. But this is not really, doesn't allow you to really tap into the power of core level X-ray spectroscopy or soft X-ray spectroscopy, as I tried to highlight to you. So the challenge is to push this to higher photon energies so that we can access these 1s electrons, these K transitions or maybe L transitions. And so we need two ingredients. One is to use the lambda square knob. So we have to build lasers at 2 microns or longer. We did this. And then another thing that was not so easy is for phase matching. For this to happen efficiently, the generation of attosecond pulses, you need high pressure targets. And you need some ridiculously high pressures of, let's say, 10, 12 bar. Why do I say ridiculous? Because you need to confine them in maybe a millimeter, 1.5, and then this gas streams out into your vacuum chamber, and you want to keep good vacuum. So you have to deal with the fluid dynamics, but you can. And if you do, you can generate radiation as shown here on the top left on the plot labeled B, which, for example, covers directly the whole water window range. That means between the principal absorption edges of carbon and oxygen, and it contains also nitrogen at around 410 eV. This is a linear scale, actually. We spend a lot of time characterizing these pulses. There's a lot of controversy on this in general, I would say, and I'm happy to explain why. If we trust all these measurements with general techniques, which I would be a bit wary about sometimes, we can put the record here on 23 attoseconds. We tried to be careful and rather put an upper limit of 165 attoseconds, which is still short enough to probe whatever we want to see. The spectra that we get corresponding to these pulses are really broad, and depending on the laser wavelengths with which you drive them, as you can see, can cover easily across the oxygen edge, however, not with a lot of photon flux. So mostly we tuned it to 1.8 micron because we want to do pump probe experiments. And then we measured, for example, at the titanium edge or others, and I'll show you the results thereof. We also spend a lot of time characterizing this source because we like to talk with X-ray spectroscopists at a synchrotron, and they ask, okay, what's the brilliance of your source? And we tell them, well, we have so many photons per second. That's not exactly the same. The brilliance that we have, this is the number in the red box in the middle, is actually comparable to the brightest synchrotron slicing sources. However, we have very short pulses, and we have perfect synchronizability between pump and probe. By the way, the picture on the bottom left shows you, it's actually beautiful, I think. It shows you this, the laser pulse comes from the top left corner, goes through this target, and you see actually the plasma jet glowing there, in this case for helium. And this is exactly where we generate these attosecond pulses. We also characterize the stability at the carbon edge. That's the plot on the top left. And you see, yes, there is a little drift, but within 1% over 16 hours. So the source is stable enough to really do experiments. And then another thing that hasn't really been tapped into, and think about now transport of charges in materials, is that you can actually cover multiple edges at the same time with this broad coherent spectrum, right? We do not have, let's say, just a nanometer or an EV or 100 milli-electron volt or whatever you want to have that you have to tune in an hour or so. We can cover this at once. And so I show you some of our measurements here on HBN or on titanium disulfide. We have done time resolved measurements on titanium disulfide on a TMDC. And how that works, for example, is that you photo excite, and when you move charge from sulfur to titanium, you will see that the absorption increases on the sulfur, but it decreases on the titanium, in this case, because of the selection rules. So you can really infer where the electronic density moves. Okay, let's get to the results, what we can measure. I give you two examples. One on a solid, one on a molecule. The molecule is unpublished yet, but you can find it on arXiv. So, for example, graphite. Graphite is probably one of the most looked at materials. It basically consists of layers of graphene, if you will. It's, I would say, a prototypical semi-metal. There are many, many thousands of papers on there. You find graphite in many places, for example, in your lithium-ion batteries. as electrodes. And if you have intercalation of lithium that doesn't go back there, it actually reduces the reversibility of the charging process. So there are real world issues related to that, and people are looking at this, of course. So if you look at the literature, what you find is that this material has extremely high carrier mobility. And in fact, it's a very bad example to try our technique because it challenges it to the maximum. Why? Because it has essentially dynamics on all time scales. On the very fast time scale, on the femtosecond, few femtosecond, to the picosecond. It has all kinds of different dynamics that is interlinked. And so it actually still presents open questions on some of the carrier scattering dynamics, right? How do carriers scatter? Where do I lose basically my excitation when I excite the material with light? And then where does the energy go into the lattice? Through which phonon channels? And so let's see if we can try to address this. So very quickly, again, this is a view of two of these layers with the numbers on the spatial scale and so on. And I've also shown you two Wannier orbitals. So this basically shows you the electronic density. And then if you calculate the band structure here, I show this color-coded in terms of the momentum resolution. So for example, you see in the middle at 0 on the vertical scale, this is the Fermi level. And at K for graphene, you would have these famous Dirac cones. So this is basically where the valence and the conduction band meets. And the character of these bands, the state is a PZ orbital, which is the bottom one there shown on these layers that I have. And if you look a little bit higher, for example, 7.5 ADV up, you have higher lying bands. So these are anti-bonding states. You see there's a mix between red and maybe light blue. So these are these sp hybridized states. And if you now look at the density of states, you basically integrate over K space, you see the density of states here. Why do I explain it in that detail? Because now you can calculate or identify them. These states, the pi star states. So if I probably excite with visible light, or with infrared light, I move carriers from the pi to the pi star bands or states from the valence to the conduction band. I also show you down there in the red line, the innermost bound electron, the 1s electron, which is bound by 284 eV. And we can access this, of course, with our attosecond radiation. And you see these two bumps in the density of states. And in fact, they directly relate to these Wannier orbitals. This is why I plotted them for you here. What this means now is if, for example, I have a lattice vibration, right? And let's say the lattice vibrates, let's say in plane, then this should register on the sigma star feature, even though I might not excite anything. So what I'm trying to tell you here is, let's say the power of this is Coulomb coupling, right? Each atom has electronic states. They all talk to each other. They're coupled through Coulomb forces, mediated through Coulomb forces. So if I have a lattice vibration, I change the electronic states. I shift them, for example. If I excite some states, of course, I do the opposite. I might change the lattice. I start a phonon. And so if I now do not only look at the close to the K point, but I can have a large range of energies simultaneously interrogated, I can think of using these as fingerprints where I, for example, don't excite, but I see changes. Right? If I do absorption measurement and I measure pumped minus unpumped and take the difference, I can see a change there. For example, in the sigma star, it tells me something about a lattice vibration or a change in electronic states. So now if I use my attosecond pulse that I have shown to you and I probe this, so there's no pump, it's just probe, you see on the right, I get the black circles. Again, why does this match so well? Well, because we use just one electrons, one electron that can go to any p-type state, and therefore I can have an unambiguous mapping between photons and electrons. Okay, so this gives us the confidence then to really look at what's happening here. Okay, so I have to probably speed up a little bit, but I show you now the differential absorption spectrum. You get the pump probe parameters up there. again, is differential, so it shows changes compared to unpumped. And if I now analyze this and take lineouts out of this, I can see that I have photodoping in the vicinity of the K point. I can get the broadening and splitting out, and depending, we pump this for a huge range of pump parameters. You can have large effects, or you can just have little excitations. However, what I like to point you to is the fact that we can get electrons and holes, and we see changes up there at the sigma star where we are not exciting. So it shows already through the different time scales that is a different mechanism. And I just show you the incoherent background. So what actually happens is that during the light field that's excited, you induce a polarization. I call this a coherent excitation that then dephases into a population. That's the incoherent background we measure. And then that might couple to the phonons, and similar things happen. We also have theory support from Sangeeta Sharma on this with real-time TDDFT, and they actually could nicely confirm the story that I'm telling you here. So we get the real-time electron and hole dynamics out. We can directly read out parameters like the chemical potential, the carrier concentration, and so on. And again, I emphasize it's nice that we can look at electrons and holes. So what about these two questions? Well, one of the big questions here is which scattering mechanisms? Do I have, when electrons scatter, it can happen that, for example, one electron has then a higher energy, if you will, and actually one is annihilated, or so this would be Auger heating, or you could have the fact that one electron knocks another one out, loses a bit of energy, so you have more electrons, but at a lower kinetic energy. So this would be good for a solar cell. So what's happening here? I show you results from the two measurements, different photon energy, but similar flux. I know this is a complicated graph, but just bear with me. If you look at the top right, you see, for example, the blue circles are the number of carriers of electrons, and you see they basically go up, whereas their mean energy goes down. These are the turquoise dots. If you look at the left at this Dirac cone that I was plotting, this is exactly the signature of impact excitation. The number of carriers goes up, but their mean kinetic energy goes down. And it's the same for holes. If I change the photon energy to 2 microns or 1.8 microns from 800 nanometer, you see it looks a lot more messy. There is a competition between the different processes. If you think about it and analyze it, you can understand it in the sense that this material is n-doped, so the scattering phase space is not symmetric, and this gives rise to this competition for one carrier type and not necessarily for the other. So with the X-ray method, we can here directly get out and identify, in fact, the scattering mechanism. So we can answer the first question. What about the second one? Well, how do electrons couple to phonons? And in this case, I show you out of these let's say 6 Dirac cones, if it would be graphene, right? I show you 2 of them. And there are 2 phonons, strongly coupled optical phonons, that are always discussed. One is Raman active, one is not Raman active. It's called a displacive one. And this is typically thought that is not that tremendously important because it takes longer and so on. There is a symmetry change involved. And now if we analyze this yellow curve that I show you on top, which is not from a direct electronic excitation, but from nuclear motion, and I do a time-windowed Fourier transform, I can try to see actually what is happening here, right? Because this is not polluted by the direct electronic excitation. And so what I get is something like this. I have a terahertz frequency on the vertical and the time delay on the horizontal. And if I just integrate it over the time delay, I get in fact the phonon frequencies out, and I can identify these 2 phonons with their frequencies. But I can also see that they're in fact both active at the same time and they maximize at a similar time, and I can identify them through a calculated phonon band structure as shown on the right. And through theory, together with Martin Garcia and Kassel, they have done this for us. we can actually identify that are both active because of the very strong electron-phonon coupling. And in fact, the non-Raman active one, the one that you wouldn't see in Raman spectroscopy, which is one of the standard techniques, actually takes about 90% of the energy away, and funnels is the main loss channel in this case for our excitation fluences and photon energy. So we can really address this question. I know I don't have a lot of time, but in fact, I'm out of time, but I want to still show you something very similar ideas, but showing to you that this method is agnostic in terms of what you're looking at. You can, of course, apply this to chemical dynamics. One of the big questions on these ring molecules, on these heterocyclic systems is, for example, if you photoexcite them, where does the energy go? Does it start just wobbling, basically? This is this ring puckering dynamics, or does the ring break open, and can we follow how this opens? Why is it important? I show you here a complicated, let's say, cut through the potential energy surfaces, and there are different singular points which are called conical intersections. These are basically gateways from one potential energy surface to another one, and this is very important, for example, in your body to prevent DNA damage. It's important for retinal isomerization and many examples. So can we follow this? Can we identify and time these conical intersections the whole way? Okay, so what we can say here is this is the measurement, again, differential absorption measurement, and we can try to analyze this, and we do, and what we get out of it is, for example, in this case, we didn't have UV excitation, we used infrared pulses. We know that we're exciting predominantly with high confidence the pi star potential energy surface or state because of the oscillator strengths that we have. So we know the starting condition. Then in principle, the electron wave packet splits. It can go one or the other way and on its reaction pathway. And when it goes through this conical intersection, basically you have it starts with the same phase, but then the electron wave packet splits. One goes part on the upper energy surface, one on the lower one. And then due to their mutual coherence, you would see quantum beats. And this is the way how we can actually analyze this and get out what is happening in time. Before I do this, I want to also show you that the method is sensitive to symmetry. So I show you up there on the right, distorted static absorption spectrum, and it shows you the edge, the absorption edge. So on the right is basically the continuum, if you will, and you see fear and experiment match quite well. If we now pump the system, and in the earliest time, you see the graph below in blue that says 10 to 10 femtoseconds. It's integrated over that time range. And I see a singular occupied molecular orbital peak appearing. That's the one that's dashed dotted between red and orange. Why is this? Because now, if the molecule is still intact, I have a hole that I probe, but the two carbon atoms, the C1 and C2, are non-identical. The C1 is closer to the oxygen than the C2, so they are slightly shifted in energy. We cannot resolve this here with our spectrometer, but what this shows here is by having one of these peaks that the molecule is intact. Without knowing anything about the rest of the molecule, I know it's still intact. And what I can then do is analyze in time following and see what information I can get out of it. Okay, so if I do this, I can analyze these oscillations in the absorption spectrum as function of their energy, and I can directly do a Fourier analysis of it, and I see actually different terahertz frequencies. And what I can actually identify them with is these quantum beats that I told you about, because what's happening is that the electron wave packet goes through the conical intersection. I can show you this up here on the right. So when you have the vertical transition, I launch a wave packet, it goes through this first cone. I can even time this. This happens in below 20 femtoseconds. In fact, in 12 to 16 femtoseconds. Theory says in 12, we measure at 16. That's in pretty good agreement. Then shortly afterwards, it goes through the second cone. You see this indicated by that first black arrow. And that again resets the time, there is a shift in oscillation frequency, which is indicated by the change on the top left from the blue box to the green box. And then this decays very quickly. Why does it decay quickly? Because the potential energy surfaces, their distance increases very rapidly. This is shown here on the right on the S2 and the pi sigma star potential energy surfaces. So by just analyzing these quantum beats, I can actually time when the different conical intersection happens, and actually together with theory, again, in theory, it says 60 femtoseconds roughly. We measure it in 80. I would say this is in pretty good agreement. I can see where the system evolves to. Now, I'm nearly at the end. This is what I just showed you when the system is intact. If I look at the later time in my absorption spectrum, forget all the time-resolved things. I see now immediately that there are 4 peaks. There are 4 peaks below the absorption edge. Why is this? Because this is, in this case, where the molecule has broken apart. So none of the carbon atoms are identical because they're all at different positions and their binding energies are relatively shifted, and I can see this very nicely. I think this is a great visual way to see directly what's happening here. And so this is why I think X-ray absorption spectroscopy or soft X-ray absorption spectroscopy is actually so powerful to combine with the attosecond science. So I know this was maybe a bit quick on some of the physics. Feel free really to contact me or to ask me anything. I just wanted to give you a flavor about the motivation, and by the developments of the attosecond technology that was also mentioned in the Nobel Prize committee yesterday, that we can really try to look at these long-standing problems in a new way and add a new potent tool to the arsenal of spectroscopists or chemists or material scientists. So if you're interested, I told you how to make these attosecond soft X-ray pulses at high photon energies. I told you on 2 examples how to look at these coupled electronic and nuclear dynamics. And I can't resist to make this claim here. There's a lot of things that we can look at. It's actually difficult to choose what we should look at. And there's a lot of opportunities with these different fields to collaborate and hopefully break new ground or bring new insight to it. And I think this will be really transformatory, for example, to look at phase transition and things like that. So lastly, I want to thank you all for listening, but especially to my group. I'm blessed with wonderful bunch of people that actually work very hard to make this happen, from the laser building to nonlinear optics, to do the attosecond science and to trust me with these long experiments sometimes. And of course, I also mention a wonderful range of collaborators over the last 10, 20 years, from which we have benefited greatly. And I hope I could, show you a little bit the excitement, not just because of the Nobel Prize, but because I think what can really be done with this technology to address some important and long-standing questions. And it's not just fundamental science, it can also really bridge, hopefully, into applications and not only in 30 or 40 years. So thank you very much for listening to me.